I'll just wait a bit until some people hopefully show up. All right, I'll get started in just a second. Just want to give people a chance before in case people want to get the beginning, because I plan to go over CCC for people who weren't here from when I started on Thursday. So I'll go over uh, sort of what we did previously, and then I'll go over what I did last night, because I did maybe like 2 hours of work after I shut down the stream last night, which got everything into a fairly complete state for at least the initial version I wanted. Um, so I mean, I can run it right now actually. Okay, so it's tracing, and now I'll run my old B-tree benchmark, if you guys remember from a few weeks ago. So I cranked up. This is doing like 100 million inserts and deletes, so it's going to take a while to finish. Um, I guess we'll give it like, you can do fairly long captures, so maybe we'll do a capture while we wait for people to file in. But yeah, you can do really long profile captures and then query them after the fact. What I'm working on, well, I'm trying to kind of show where I ended up with CCC last night, and CCC is the profiler I wrote, sampling profiler based on UTW, and I put maybe like 12 hours total of coding time into it. It's already really far, honestly, like in terms of functionality. It doesn't have a good user interface, but can generate text files that contain reports on standard kind of call stack profiling data. And so I kind of want to show where that is, and I want to link the gist where I have the current code up if anyone want to play with it. And then I want to jump into a new mini project, because kind of my plan with doing these streams is, I mean, partly it's to entertain myself and learn something, but it's hopefully also to teach something to people who, I don't know, maybe they're just interested in the kind of things I'm working on, or maybe they're just beginners in general and want to see how I do things. But I don't necessarily think doing, I really respect what Casey is doing with multi-year handmade hero type projects, but uh, I, personally, I don't have the motivation to do that, and so I will try to focus on some mini projects that I can knock out in, less than a week of on and off streaming sessions. That sometimes means I won't make a finished product, but I'm hoping to front load as much as of the cool technical work as possible, so that we don't have to slog through too much tedium and we can get to the meat. All right, so that thing finished. So let's set the trace. Incidentally, that trace file was so you can see this temp ETL file is 67 megs, so that's quite a hefty trace file. And yeah, or it already finished a long time ago for processing. We can actually see how long it took. So yeah, so I did. Oh, is my mic cutting out? Could anyone else? All right. Let me know. Also, let me make sure that my whole desktop is showing. Yeah, it is. Um, but anyway, so yeah, I ran the trace of B-tree, like a big meaty benchmark run. Um, it was, like I said, it was a 67 meg dump. So very, very hefty dump, a whole lot of data. In order to load it from disk and parse it, it only took 1.7 seconds. In order to symbolize it, it only took 330 milliseconds. And so here below we actually have the exclusive and inclusive breakdowns in sorted order. So you can see that even though we're actually benchmarking these add and remove functions, we're actually spending a whole lot of exclusive time in run benchmark itself. And that's just because we're doing a lot of iterations rather than doing a few big operations. I mean, on a B tree, any given operation is going to be fast. So we're doing like 100 million operations. And because of that, we're actually spending a lot of time in the loop itself rather than inside the worker functions. But yeah, so you can see there's a bunch of work here, and then you see these functions that do adds and removes. They're near the top of the exclusive, and then there's a big drop off. So this is like a very typical top-heavy exclusive time breakdown. And of course, this is not a real program. This is a benchmark. And it's a benchmark designed to benchmark add and remove. So it's not surprising that these eat up the lion's share of the time. So that's the exclusive breakdown. I also have the inclusive. And the way inclusive works, if you guys are not familiar, is that anytime you sample a stack and a given function symbol occurs on the stack, whatever time slice is attributed to that stack is also attributed to that function that occurred. And so what you'll see, of course, is that the top level functions like winMain and runBenchmark are at the top because everything else has them on the stack. And then you have this breakdown. And again, there's a drop off. But you can see, for example, how the you can see how things break down. And then we have let's see what else is here. You can see how much time this stuff is spent. And I also have aside from just doing counting time, I also have like a per sample breakdown. Like here's the number of samples that were taken with the run benchmark on top of the stack. Here's the number of samples that were taken where winMain was on the stack. So you can see we took around 105,000 samples total that hit our process because that's when winMain will be on the stack. It'll always be on the stack when our stuff is running. But anyway, yeah, so this is like a typical call stack oriented profiler. Right now, I don't have a query that shows callers and callees for a given symbol, but that would be like very trivial to add. Just to explain how I ended up at this point from where we were last afternoon when I signed off the stream. At that point I had an exclusive. I did basically I had basically this thing printing the exclusive counts. So it was doing a counting, but only for the not in time, but just in samples, and it was only doing it for the top of stack symbols. So after that, I added inclusive counts first of all, which the way that works is actually really simple. When you're doing the symbolization and you're processing the call stacks, so this is the big function that loops over all the stacks we've collected. Discard skips any that are not for the process we're interested in, then loops over all the function pointers for that stack. Here's some stuff to do, sort of lazy symbolization. Once we get here, we have a symbol resolved for the instruction pointer on the stack. And then there's two cases. If j is equal to 0, it means that the symbol is at the top of the stack. In this case, we increment the exclusive count, and we add to the exclusive time for that symbol using the stack's time span. So the time span accounts for, the estimated time that this stack it's a sampling profile, so it's not really the amount of time the stack was running, but it's the quantum of time attributed to that stack sample. And then here we do the inclusive accounting, and basically what we do is we have a parallel array of these last stack pointers, where for a given symbol we can figure out what was the last stack that symbol was seen on. And so that way, if we see a symbol multiple times on the same call stack, and this occurs in the B-tree program, for example, because you have a lot of recursive functions, you don't double count. So yeah, this right here is actually the entirety of the inclusive and exclusive accounting, which I think points to the fact that probably I set up the data structures pretty well when you can do inclusive exclusive counting this easily. One other thing I added was this time span thing. So previously we could only do kind of discrete counts of how many samples we were seeing for the exclusive count that I showed on stream last night or last afternoon. Um, so the thing I added is now every time you get a new stack sample from ETW, I assign the time span based on the last time we got a sample on that thread. So we don't assume, even though we're sampling at an estimated 1,000 hertz, we don't assume that every stack sample corresponds to exactly 1 over 1,000 seconds, which is, I guess, 1 millisecond. We actually use the the timestamp gap between successive samples on a given thread to assign that time span. So that was another thing I did. And I also did a bunch of cleanup. I think actually the code shrunk by 150 lines of code yet relative to yesterday, mostly because I went through and removed stuff that I actually wasn't using anymore. So for example, um, I'm actually not using the raw profile events. I'm only using the sample events. We still need the profile events to be captured because the stack events are generated as a side effect of the profile events. But the only events we actually use to drive the profile analysis is the stack events. So you'll see there's no longer any event underscore profile sample the way there was yesterday. It's all in this event stack walk case that does that. Let's see what else we did that I didn't do on stream. Oh yeah, the other thing, I mean, maybe not very interesting, but maybe worth mentioning at the same time, is that once I started doing this time accounting for the time spans, I had to figure out what units of time were actually being used, and that led down some annoying bugs that I eventually fixed. But basically, when you do the initial profile capture, you set this client context variable. For some reason, there's no enum for it, but one means basically that you're using the query performance counter timer to tag all the events. But then separately, it's not enough to do this, because what I found is that oh yeah, so anyway, so you set this, and that tags all the events with QPC counters, and then on the trace processing side, which I guess is here. First off, you can read this perfreq log file header field. This is basically the equivalent of query performance frequency, but not for the machine that you're on, but for the machine where the trace was captured. Now, in my case, that's the same machine, but doesn't have to be. So we pull that out, and I thought that was enough. And then you can divide by this to convert counters to times. I thought this would be enough. The problem is it was implicitly converting all these QPC values on the timestamps to Win32 file time. So that was throwing off my numbers by like around 3x, and that was super confusing, and it was not very debuggable. But after thrashing around and just reading a bunch of header files and docs, I found out that if you set this flag on the event trace log file as you start processing, it will basically give you the raw timestamps and QPC values, and then when you do the division by performance frequency, everything worked out. So after that, all my numbers on these inclusive and exclusive times were perfect, basically. And one way I validated that was I opened the same ETL file in different ETW analysis tools and verified that they matched up to the second decimal, and they did. So because of that, I'm going to say that this is basically bug-free for the feature set that's in there. It's very high performance for what it does. Actually, you can see that the symbolization, even for very long captures, is sub-second. Parsing takes a little longer, but that's mostly I/O, I think. And the reason I say it's mostly I/O is that if I repeat this run, it'll be like 200 milliseconds or 300 milliseconds for this parsing step. It generates these exclusive charts. And really the main thing I would want to generate next if I wanted to make this into a more full-fledged tool would be call trees. But in order to do that in a nice way, I really need an interactive graphical user interface, and otherwise they're not worth a lot. And so I don't necessarily think that's an interesting problem to tackle on stream. And so I'm going to leave it at this. If anyone wants to take it further, and I may do so in the future as well if I find a pressing need for it, I encourage you to Go look at the latest code, which I posted. Okay, I guess I should. Well, maybe I'll make this public later. Um, but you can go to this one and you can read the code and maybe play with it, run it yourself, and let me know what you think. And if you want to build your own tools on it, go right ahead. I would love that. I gave a copy to Sean McGrath, so hopefully he'll do something with it. I think integrating these kind of tools in game engines would actually be super useful. Um, if you guys have ever used tools like telemetry or remotery or any of the number of kind of in-game interactive profilers people write, you could write something like that using ETW in real-time mode, and without having to mark up your code with zones or anything, you could actually get this kind of data in real time on charts. So that would be super cool if he does that or someone else does that. But anyway, so I think I'm done with this project for now. This was like 12 hours of coding. I think I got where I wanted. I'm not, it'll probably take, if you wanted to make this into a full-fledged tool, it'll probably take around 10 times as long, and the technical density of the work would not be very appealing. So I thought I would move on to another problem, or not, another mini project, also sort of a low-level systems mini project. And so the genesis of this is there are some other tools slash mini projects I'm thinking of writing, and then one of them is a debugger, like just a Windows 32 debugger from scratch. And in case you guys, well, I haven't written a full debugger before, but I have a pretty good idea of what the technically meaty parts of a debugger are that are not built into Windows itself. And the two pieces are an x64 disassembler, and the other one is a sort of expression evaluator or data evaluator. Those two things are kind of the core pieces. The expression evaluator doesn't necessarily need to be like compatible with the C language, but it needs to at least be expressive enough to let you talk about any C style types, right? Like structs and unions and arrays and pointers and all the various primitive types like uint8s and floats and whatnot. And so and 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 so I thought I would write a little library with hopefully like a nice API, probably hopefully nicer than most of what's out there, assuming there's even anything quite like what I want out there, which you could use for doing things like low-level expression evaluators for C-style data structures, and something you could also use for things like foreign function libraries. So not just something like an expression evaluator and a debugger, but maybe also if you have a scripting language and you want that scripting language to call out to third-party libraries, you typically need what's called an FFI, a foreign function interface. Um, the thing I'm going to work on, I'm actually going to start not with the foreign function part, but with the foreign data part. And something like this is also used, for example, in reflection systems in games. If you want to directly interact with data structures in memory with like maybe a UI or something to print or manipulate values. So I thought I'd write a nice little library for that. And I actually started sketching already, like how a lot of these things start for me, especially with APIs, is that I'll just start sketching in Notepad. There's something formal about opening a Visual Studio project, but often I'll just start sketching in the Notepad and go from there. So yeah, I kind of wanted to kick that off formally. So far, I haven't compiled any of this code. I've just been sort of sketching it out, and so I thought it would be cool to kind of really start from scratch with some of the sketch code I wrote. So let's shut down these old projects. We'll keep that open. This freaking thing. Man, this thing is being a little bit awkward. Okay. So the project is called Ceno, which is a terrible pun that I'll explain in a second. for me, I'll often think of stupid names before I even know what a library is supposed to do, and I think this was one of those cases. Um, let's just get that compiling as usual. All right. Yeah. So Ceno. I mean, I guess it's a pun. It's based on the idea of foreign data or foreign function. Ceno meaning alien in Latin. Uh, I remember there was a language I used to follow a number of years ago called Factor, and it had a foreign function interface library called Alien, and so I thought that was a cute name. And so this is I guess like one step removed from that. Um, yeah, so Alien was their Factor is a really cool language if you guys are into programming languages. It's sort of it's a concatenative prefix language. So superficially, it looks a little bit like Forth, but it's really more like Smalltalk or Common Lisp in terms of the development environment, runtime, and look and feel of the libraries themselves, as opposed to the syntax. But anyway, yeah. So so the core thing, and like I said, I'm going to start with data and get to functions later. Functions are a little bit more nasty because I have to write assembly code, whereas I can do the data part just in C. Um, right. So um, really, the core thing that you want to do with a library like this is you want to have a data structure for describing types, um, and that's what Cenotype is. And so the idea is basically like take any C type you care to mention. Could be primitive types, could be aggregate types, structure unions, and they could be nested. There could be arrays in there. There could be pointers in there. No function pointers for now, but although if the function pointers are just to be treated as void stars, that would work too. And so you want some sort of recursive definition of what a type is. And the recursive definition has to bottom out in these primitive types. Like you can see I have UN8s, UN32s, and UN64s defined right now. Um, and so, I mean, in terms of how this is defined, I think this is pretty much how anyone would do it. Um, a type has a kind, and a kind can either be primitive or it can be non-primitive. If a type is primitive, then it's I don't have all the basic C types in here, but for now we just have uint8, uint32, and uint64. And I have uint as a synonym, but not as a separate type. And then I have these two other types that are non-primitive called pointer and aggregate. And these refer respectively to pointer types and to aggregate types. And aggregate types are things like structures and unions. And one of the interesting things about this kind of low-level type system is that it doesn't have to distinguish between structs and unions. So the fact that the fields overlap in a union, it doesn't care. It's actually the same code and the same data structures. If you're doing like a fancy optimizing compiler, you do kind of have to know about that stuff because of aliasing. But if you're doing things straightforwardly, you can actually treat those as just instances of the same general notion of an aggregate. All right. Um, so if you have a pointer, if kind is pointer, then this pointy subtype will be the inner will be the type of the inner type. So for example, if the type is int star, then the outer kind would be Ceno pointer, um, and pointy would be, I guess what below I would write like Ceno int, some primitive type. Um, More interesting case is when you have a struct, in which case you have a bunch of fields, and each field has a type itself, a name, and the name is really not for data access. It's mostly just for kind of high-level debug info, but very useful for sure. But very importantly, a field has a type and it has an offset, and the offset is relative to the parent. So 0 would mean the same offset as the parent in memory, and 4 would mean 4 past that, 4 bytes past that, and so on. Another interesting thing, and you'll see this. So here's one question. What if you wanted to represent something like uint8 16? So it's a static array of 16 uint8s. There's different ways you could do this. If you're doing a higher level type system, you might have a separate kind for static arrays. So you would have Ceno underscore array or something like that. The way it's traditionally done in C compilers and other systems languages that work at this level is that actually, in some sense, every type is an array type. So that's what this count field that's what this count field does here. The size field refers to the sort of element size, and the count is the number of elements. So you'll see here where I'm initializing these base types. Size of is the size is size of an uint8, and then there's a count of 1. So the basic idea is that in C, well, not really C, but sort of the machine paradigm that C is based on and machines actually work with. There's no difference between a uint8 and a uint8-1. If you think about it, because they're both just the same layout. You access them the same way. And so we're kind of going to abuse that by flattening one level of the type definition and just having essentially all types be potentially array types. And it's just that the common case is that they have a count of 1. But anyway, so that's a little bit of a simplification, but kind of a useful trick when you're dealing with machine level type representation where you don't necessarily care about capturing the high level intentionality of the type definition, but you just care about having enough structure there that you can you can read the bytes and make sense of them. All right, so that's the types, and that's really the bulk of this data structure. The other thing is Ceno data. So Ceno data is essentially just an opaque pointer combined with a type description. So if you had a local variable in C and it was a uint8, and you wanted to construct a Ceno data to describe it, you would do it like this. So that's how you would do it. So in other words, you never represent data with the system by value. You always have the thing that describes the data always has a pointer to the value. And in order to make sense of what the memory is behind that pointer, that's why you attach this type. So that's the idea behind this overall scheme, that you always pass around pointers along with types to describe their interpretation at the machine level. So that's the basic idea of the data structures. Let me go over some of the API. I think it's pretty simple and easy to use and straightforward. So as always, I always start with assertions, data structure invariants. And so when I wrote this, I'm like, okay, let's figure out what things have to be true of a type to be well-formed. Well, it has to be a null pointer. The other thing I'll mention is you always refer to types through pointers, and the reason is types can be recursive, so you couldn't contain well, you could in some cases you could contain them by value, but in general you can't. So they're always referred to through pointers. So for a type to be well-formed, well, the pointer itself has to be non-null. The kind has to be in the valid range. It has to have non-zero size and non-zero count. So I thought about this for a sec and whether it's ever legal to have zero size. I think it probably is, but for now I'm just going to leave it like that. I don't think you can ever have size of x equals 0 in C, but I know that in C++ there's some weird stuff with empty base class optimizations and things like that where maybe you'd want something like this. But in any case, I'm going to leave this stronger invariant for now. If the kind you're dealing with is a pointer, first off, you make sure that the size is actually equal to the pointer size, which is 8 bytes on 64-bit, for example. And then we recursively assert the type, check the type invariance for the underlying type of the pointer. If we're dealing with an aggregate, which is like a set of fields, then we go over all the fields, we recursively check their field types, and then this one is a little bit interesting, but makes perfect sense if you think about it. The field itself cannot stick out past the end of the parent size. Actually, this is right. So the field offset plus the field type size, which is the end of the field within the struct, cannot stick beyond the aggregate's own size. And then finally, if we have none of the above, then we have a primitive type. And what we do is we use the kind index into a table, which gives us, for primitive kinds, it gives us the canonical type representative of that kind, and we verify that we have the expected size. It doesn't have to have the expected count, because we can have, for example, like I said, you can have something like a uint8 16. That the size would be 1 because it's 1 byte, but the count would be 16. We don't require the counts to match because of that. All right, so that's the basic description of the data. Then there's a bunch of accessors. You have, well, first off, this one, which is just for resolving names to field indices. There's this one, which is basically for doing pointer arithmetic to traverse the type description. So you're kind of traversing the type definition in parallel with the pointers that point into the data. So for example, if you have data and you have an index, then this is essentially just adding the index times the size of the data to get a new pointer, and it has the same type as the old one. So for example, if I have this, or let me use one of the types I actually have to find. If I have this, and I do effectively, well, so actually let's write it out in full. So if we have this, and we do Ceno get element, let's see, Ceno data, x3 data. If you do this, that essentially gives, so essentially that would give you x3 data equals x plus 3, or the pointer for that would equal this one. So this basically just does pointer arithmetic in the units of the type, right? So it's the standard way that C does pointer arithmetic, not by bytes, but by the size of the underlying type. So it does that. If you guys have ever used LLVM, there's something in LLVM called get element pointer. Which is basically for doing sort of array and aggregate arithmetic, so it does something similar to what I'm doing. It does the same thing. Basically, it does the same sort of thing. I shouldn't overstate it because there are probably differences I'm neglecting, but it does the same sort of thing. So yeah, this is basically for navigating static arrays. Once you have or not even static arrays, once you have a pointer to the base of an array, this is how you do pointer arithmetic in the natural units of the type. Get field is sort of the same thing, but because an aggregate is not this homogeneous collection of the same types over and over back to back in an array, but it's a heterogeneous collection of different fields. The index now is not just like, we can't just multiply the index by the underlying size. We actually have to look up the index or we have to look up the field's offset and do it that way. We also then update the field type to point to the we update the resulting type to point to the right field type. Unlike this case up here, where because an array is completely homogeneous, it's just always the same type, which is data.type in this case. So that's it for basically the sort of pointer arithmetic where you're traversing the types in parallel with the pointers. Now we get to the stuff that actually reads through those pointers in the Ceno data structure. So the most basic one perhaps is to dereference a pointer. If you pass in a Ceno data that describes a pointer type, you can see we assert it right here, then essentially we create a new Ceno data, which is the pointee, the thing being pointed to, by just doing this simple, we cast it to a void star because we know we know pointer is a pointer to a pointer, and then we dereference it and assign it over, and then we unpeel the pointer's type to get the pointee type. So this is how you dereference. So for example, suppose I had a uint8 pointer in C, and maybe this points to a byte somewhere. The Ceno data for this would be would be ampersand p. So you can see that because of this, this is a pointer to a uint8. Of course, this gets cast down to void star in the Ceno data structure, but conceptually that's what it is. And then we have to specify the type, and the type is well, we have to make a new one. So this would be Ceno pointer. I can't remember the field order. Ceno pointer name size count. So Ceno pointer name, and we can call it p, but that's not strictly necessary to assign it a name. Size would be just like size of void star, and count would be 1. And then this would be this would be the thing here, and then we have to also have the pointee. Let's see. So that's where were we? So this is data and type. Oh wait, no. We need also something beyond this. We need also the pointee, which would be Ceno uint8. Right. So this would be how you take like a C-style data structure and reinterpret it as this sort of reflected data, or this reflected type and data representation. And then given that we now have this, we now want to do the equivalent of like reading from P, right? So we want to do basically like the equivalent of this operation, dereference P and assign it to something, or be able to read from it as a uint8. And so at that point, the way you do that is you would do, let's just call it B for byte. You would do Ceno dereference, and we provide the destination argument as the first one, and then like this. And so at this point, B data type kind would be, well, I guess actually concretely it would be equal to this one. And we could also assert that if we actually, if we now went and dereferenced that pointer, we would get, or actually, I guess I should say maybe more like this. This equals the original byte pointer. Or put another way, yeah. So anyway. Kind of like that. So that's how the dereference function works. Hopefully that makes sense. Should be pretty straightforward. Most of these things correspond pretty closely to how you do it in C. Copy is just a memcopy straight up of the underlying bytes. So there's not much to do there, but obviously this is a useful operation if you just want to copy stuff without knowing what it is other than its size. Then there's cast, which is pretty interesting. Cast is one case where you can't. So first off, let me mention there's two kinds of casts you might possibly do, and these actually also occur in C. So in C, when you do something like, what's an example? If I have a uint, if I have a uint8, and I have a pointer to that, and I can cast it as a pointer to another, like a pointer to a bigger type, for example, and then I can try to dereference it. I guess this is a word. I can try to dereference that through the casted pointer. This form of casting does not do value level casting, right? This essentially just reinterprets the bytes. So in this case, for example, I guess on little endian machines, this would fill in not only it will fill in the lowest byte of W with B's value, but then it would also grab the 3 bytes after B in memory, which would actually be, I guess, the lower bytes of this P pointer, which are fairly, there will be like part of some stack address or something, and it will copy those into the 3 higher bytes of W. So this kind of cast is, I actually don't know what people call it, like maybe like a bit cast or a raw cast or something like that. Definitely useful. I mean, one case where you use it is like in practice a lot is, for example, you have a float, and then and now I know some C language people are going to yell at me because this is violation of strict aliasing. But if you cast this to if you do like this, um, which is essentially the example of what I just did before, but now using floats to uint32s, we can now basically access the bits of the float. And of course, this is very useful if you want to do like tricks directly. You want to do the standard floating point tricks of directly manipulating the mantissa and the exponent and the sign bit. So this sort of stuff is useful, but it's not really a sort of value preserving or a semantic preserving cast. Um, Now, this kind of cast here is extremely easy to do in Ceno. In fact, I don't even have a function to do it, because all you have to do, so let's take this example. If I do this, and I don't have a float type right now, but let's say we did, it would be like this. All I would have to do is do this. It's essentially the same, well, and I could get it, supposing I didn't know about the original f and I can only access through f data. I would just go through, I would get the pointer, the same pointer as f, and I would just basically, I would just use another type descriptor. So in this case where you're just casting pointers, really all you're doing is replacing the type field with something else. And then eventually when someone reads through that Ceno data, they're going to interpret the bytes underlying that pointer as whatever you said. So that's, that's sort of free in this system. That just requires you to switch the type descriptor. The thing that's not free and does require, unless you want to do machine or assembly language, actually requires help from the compiler, is doing kind of value casts. So value casts are things like if I do this, and in this case is an upcast, so you don't have to explicitly cast, but it's essentially the same thing regardless of whether you're adding those explicit casts or not. In this case, what's actually happening at the lower level is that it's doing what's called a Cero extension, where the first byte of B is now 32, and all the three higher bytes are 0. So that's the Cero extension. Signed extensions are maybe a little more interesting, because suppose I have -1 as a signed int, and I want to upcast it to a 32-bit int. So in this case, if you do you can't just do a 0 extension, because bitwise this thing is like that, and if you do a 0 extension, it's going to look like this. But unfortunately, this is not -1 in 32-bit integers. This is actually 255. So in order to do this correctly, you have to do what's called a sign extension, and basically what that entails is copying the sign bit up and replicating it in all the extended bytes. So a proper sign extension would actually do this. Anyway, so point being, you have to somehow get, and there's special instructions for this in x86. So there's move cx and move sx, 0 extension move, sign extension move. So this actually requires a different code at the assembly level to do these different operations. And so unless you want to write that directly, you have to somehow coax the compiler into generating those for you. And that was a pretty roundabout description of why we need this, but here's how we actually do it. And I'll mention something a little bit about how I chose to make this function, because there are some seeming inefficiencies, but they're there for a reason. So the most obvious way of doing a cast, by the way, like this, is to, and let me also just take a drink because I'm talking too much and getting super hoarse here. The most sort of, I guess, direct, and actually the thing I tried for about 3 minutes before I dropped it, the most obvious thing you can do, either using a nested switch or a sort of, what is it, like, you can do these sort of tricks where, I mean, we're not going to do that here. You can do these sort of like 2 dispatches in 1 tricks, and maybe you do this, right, and then you do something like this. And then you, I mean, this is, I guess, a nice trick to know, but we're not going to use it here. So you can do something like this, and then you can do like, oh, if I'm casting to a uint 32 from a uint 8, then we would do, let's see, so the destination pointer we cast to, um, we do like this, and then from the other one, we have, well, no, we do uint 8, and actually I'm mixing up the, so this would be uint 8, and then source pointer, and so you could do something like this, and then undef pair at the end here. So this would be like a standard, I think this is a fairly standard trick if you're a C programmer for doing sort of like dispatches. The basic problem though is you're still ending up with like n squared dispatches. So even right now there's like, and this is like placeholder because we're going to need, I think, something like 10 different primitive types at the end, because we need uint 8, 16, 32, 64. We need the sign counterparts, that's 8. Then we need float and double, that's 10. And I think we also need to do sign char. Char is weird in C. It's not just a byte for conversion. So we need to probably have like 12, let's say. And so you have 12 squared. You have a 12 squared matrix that's going to get pretty crazy. And so I decided that doing this thing exhaustively with switches is probably not worth it. Even though seemingly you do less work because you're only doing exactly the casts that are needed. So instead I ended up with this approach that's a little more palatable. Technically speaking, there's still n squared work because we're doing 3 here, and 3 here, but it's just not as crazy and nested. So and it's, you know, it's really fast. Like, this is not going to be an issue. So anyway, the idea behind this is there's a first part of this function that only handles converting. It only dispatches over the source types. And at this point, it doesn't know what destination type it's going to be required to generate. So what it does is it directly generates a value of its underlying type. So for uint 8, that would be a uint 8 value. And then it essentially leans on the C compiler to do these upcasts. So these assignments effectively do these zero extensions that I mentioned before. In this case here, the thing we're directly generating is a uint32. So then we have to do a downcast, which requires an explicit cast. Technically, we don't have to do an explicit cast here. That's C will do that just fine, and so on. So basically, after, oh, and also you're not allowed to cast a non-primitive type, so we assert on that. After you're done with this switch, the post condition is that all of these value variables are filled in with something that corresponds to the cast from the source value. And so once we have that, then it's a really simple matter of dispatching over the destination type and just doing the assignment from whatever one of these source values is the right one for it. So yeah, that's how you do these casts, or at least the way I chose to do them in a way that's not too much code and too expansive. So it would, yeah. So we're probably, like I said, I haven't even compiled this code yet, but I think we're gonna try to copy it in now and see what stuff is wrong. So I know we're definitely gonna need standard int. Okay, Ceno type. That's a recursive definition, so we have to forward declare it. I didn't write my assert macro, so let's do that. No include, what is wrong with me? Oh, well, it has to be the message box A for 1, but that's not it, right? Include expected a file name. Oh, I'm an idiot. Type pointer. Okay, so it's not type pointer, it's Ceno pointer. Data is pointer. Okay, that compiled. So yeah, let's try. Yeah, let's try getting it. Let's try going somewhere here. I think the other thing that would be nice to have is a print function, just for debugging, honestly. But maybe also useful in the final API. So we would like to be able to print some data, And in order to do that, we will, um, I guess we'll do a switch on the kind. And so let's see, I guess we'll do I should also compile in 64-bit because fuck 32-bit. Okay. Okay, so that handles the primitive types, and we should make sure that we don't ever hit this case. Then there are pointer cases. I think we also need to be able to print a type. So I'm also just going to do that real quick. And yeah, okay. So type kind. Actually, for these, I have a convenient trick, which is I had this table called Ceno types that I can just index directly with type kind and then get the name from that. Okay, maybe that's it. Okay, and then for a pointer type, I think you just do, and I'm going to use this kind of Lisp notation, which is convenient when doing recursive printing. If there's an aggregate, well, actually, I guess we can always just print the name. So what should be the format? If you have a uint8, I guess it should just be called uint8. But then pointers also have names. So what if they're a pointer? Maybe like equals whatever. Yeah, let's do that. So if you have a pointer type, you do maybe like this. No, I think we do like this, even though that's a... No, let's do like that. So the thing and then a pointer. And we recursively print that thing inside. And for aggregates, I guess we do the same general idea, but now we have to iterate over the fields. Well, let's see. How do we print the fields? I guess we want some sort of like, so maybe if it's a person aggregate, and then like it would be like name, string, offset 0, age uint8, offset 8. Oh, I guess this would be maybe a char star. So actually, let me use a star instead of a pointer, since it's more like C. No, I'll just keep that. Okay, so each field has this parenthesis. Okay, so that's fine. And then let's see. So first there's the name, then there's the offset, and then there is the, that's actually a big offset potentially, and then there is the recursive thing itself. So field name, field offset, and then Ceno print type, field type. And then we have to close it up. We also have to close up the whole thing. Does that work? Probably I should pull over my... Using printf is so annoying in Windows because of all the console redirection crap. I'm going to pull over my output F macro from the other one. Okay, so make sure that still compiles, and then replace. Okay. All right, so I guess before we, well, let's just finish this off for now. Actually, let's do this so that it'll assert if we forget about that case. And then I guess let's just create some types. So let's print types for the basic types. Does not. Okay. Don't want to deal with const. It's a pain in the ass. Okay. I guess I need to. Okay, so that looks right for the primitives. And then I guess next step would be pointer to uint. So Ceno pointer pointer to uint. And okay, what's the field order? Kind, name, size, count. So I should put some of these things into enum so I don't have to keep typing them. Nah. Alright, let's just do it that way. Count, and then the inner type is uint 8. So does that compile? It does. I'll also go and open up the usual trick I use for output when it gets a little bit longer and I don't want to keep glancing at it through that tiny window, is that I'll just open it. I always have my window set to auto reload so they automatically trail the latest output. Alright, let's see here. So does that work? Pointer uint to a uint, so that looks right. And you should be able to, you know, nest it further. If it works at one level, it should work at any number of levels in this case, if I didn't fuck up. So, but let's just verify it. Okay, pointer to, okay, so that looks good to me. So let's do aggregates. So an aggregate, um, let's do something like this. So since we don't have chars, I'm just going to call them uint8s. So there's going to be a name, and then there's going to be an age, and the age is going to be a uint8 as well. And so I want the corresponding type to be an aggregate. And there's going to be a bunch of fields here. And field number 1 is, okay, what's the definition order for fields? Type, name, offset. So it's just like C itself. So it's type, name, offset. I guess we can use this one. Where's that defined? That's defined in standard def, so maybe we just have to include that here. So person name, and for this one, actually that's not right because that's a pointer, so we have to, this is a case where actually our existing thing comes in handy. So that's a pointer to uint8, name, offset, person name. And then for the next one, that's just an actual uint8. So we're just going to do that, and then age and offset of, what did I do wrong? Okay, I didn't do that. And then we do this one, and it's called person, and size of person, and 1. And I guess I can just, well, this is where unions and initializer lists probably don't like each other. Right, so I'm just going to do it by assignment. So fields count is 2, and then person fields. Can't spell for shit, apparently. All right. Okay, we didn't actually print it, so let's do that. See, that looks good. Oh, let me add this one at the end again. So, aggregate called person. Okay, I definitely need spacing. So I guess the way we do that is if index is not equal to 0, we do an extra. Oh no, that doesn't work. Is that the right one? If the index is non-zero, then we prepend. Oh. I bet I'm going to make that bug again. In fact, let me remove standard IO so I don't make that bug. And then maybe we will get the which one do we need here? Okay. I guess we'll just maybe disentangle that from all the shitty macros in that file. Okay. So that looks pretty good to me. Offset 0, offset 8. And that, yeah, that all looks reasonable. So, okay, oops, I made everything large over here as well. So I think that satisfies me that the type printing is working, and that's going to be useful for debugging, I guess. And let's see here. All right, let's also try to. Okay, so let's get back to the value printing, which I guess maybe is more interesting, and it's ultimately the point of this whole exercise. So two cases, pointers and aggregates. For pointers, I guess we actually just maybe we just do that. Well, I guess this is where it's a little bit tricky. The pointee. So we have to do this, right? For the aggregate, we do that. Okay, so to print the values of an aggregate, this is maybe where it gets a little more interesting. Oh, actually, okay. I was thinking that we need to actually print. Yeah, we need to do that. Because, like I said at the beginning, all types are implicitly sort of arrays. It's just that most of them have size 1, so we sort of want a representation that works for that. So if this is not the first index, then we do a little space, and this data pointer. Okay, so I guess we should do data pointer plus index times data type size, something like that. We have to cast that to a char star first, and we have to do that all the way through. Okay, I think I'm gonna print a little bit differently depending on whether they're size 1 arrays or size 2. Because I feel like there's going to be so many size 1s that we kind of want that to be nice and flat, but then we probably want like brackets for the other case. So if the data type count is greater than 1, then we do something like this. We do that at the end as well to close it off. All right. For aggregates, let's just forget about that for a sec and do these. So let's get some data. Let's do uint8 and have 3 bytes, and these are like this. And the corresponding Ceno data will be like this. No, so like this, and then a type descriptor. Actually, that's not quite right because this needs to have size bigger than 1. It needs to have size 3. So the bytes type will be Ceno uint8. What was the second one? Bytes type, I guess. Size of person. So this is still size of uint8. Now we have 3 of them. And so that's the type we're going to use here. And then we will print that bytes data with a new line. Let's see if that works. Okay, that did not quite work. So it printed the first one just fine. So I think my pointer arithmetic is probably off on this end. So this is correctly incrementing index type size. So let's just see what's going on here. So size. What? These are very big. How come that's true? Let's see what that is. Size is 1 and then count 3. and then bytes data. That is really strange. This is like random memory. Oh, I see. No, but that, okay, that describe, I guess that describes why, well, it still works, so that can have been it anyway. Ceno type is a value, and I validated that by the time, so like here, oh sorry, I forgot you guys can't see my, OBS doesn't record those popover watches, so let's just see here. So bytes type at this point is correctly size 1 and count 3, so that's 3 bytes, and that's completely correct. Now I step over that assignment, and it has the right one here. Then I step into this, and suddenly it's garbage. What the fuck? Is it because I'm using initializer lists in some weird way? That makes no sense though. Bytes data. Let me just try something. If I do this, does it... That is mysterious. It sounds like I made a stupid mistake somewhere, but I don't know what that would be. So going through this, it's 1 and 3. Then looking at it here, let's see. So the type here currently looks right. And this is 3. This is 0, 1, 3. So initially these two are the same. And dereferencing that pointer is totally fine. Now this is 1. Oh, I see. That's fucking stupid. Okay, there we go. Yeah, no, that was stupid. Okay. The thing that threw me for a loop is when I was looking in the debugger, it looked like the count was all wrong. Like the size and count when in the pop up or pop over watches were wrong. I think the debugger was either high or somehow printf. No, that doesn't make sense. It would rewrite memory. All right. Anyway, that explains that stupid mistake. Okay, so that works. But if we print, if we just have a naked, if we have a naked byte, and it's like 42, and you can just use that directly. All right. Right. So single variable arrays don't get bracketed, but the others do. So that seems correct. All right. So let's now do aggregates. Let me just make this bigger. All right. So for aggregates, okay, for aggregates, maybe I think I'll make a separate function. Or print fields, let's say. And that will be data type fields array data type fields count. Now there's too many parameters I would have to carry over, so fuck that. Okay, so we would have to field index less than. Actually, let me pull this into a variable. Okay, and so at this point, if we say fields count, field, we should be able to. Well, first off, we're gonna do this, and for a given field, we are going to say name colon, or maybe just equals. Yeah, let's do that. No, let's do like that. Field name. Oh, and then we have to use some of our untested code for doing element access. Field data. So what is it? Ceno get field, where you pass in the field data. I guess we can just call it field. Yeah. Field data. And what else? We pass in the overall. It's a little bit awkward because of the way I compute the pointer here. Let me just restructure this loop. I actually have a function, so like rather than doing this, I should actually do get element, Ceno get element, data, data 1. Because this function basically steps it. Then we have to yeah, I think that works. I think for now we're just going to call that this. And so just make sure that still works. That doesn't work, so I probably screwed that up. Let's see, so you have the pointer. Let's step through that. Oh yeah, I guess that's the problem, that approach. So that's another, I think that's probably where I had this broken idea about multiplying by count. Okay, so the good news is the pattern of bug was exactly the same, so we only had to fix it once. Actually, I'm just going to do the data pointer directly now, so there's no confusion whether it's out of date with the underlying thing. All right, so now we can do aggregates, I believe. Field index, and now when we do get field, we can actually pass in the data itself because it's pointing to the right element as opposed to at the beginning of the whole array. And then we can do this, get field index. And then having done this, we should now be able to recursively print this. And we do the same thing. If this is not equal to 1, then we prepend an empty space. Okay, what did I do wrong here? Type should be a pointer. This is as well. All right. Didn't we have that person struct somewhere? Okay, the person struct is here. Let's say pair. And I'm just going to, for this test, I'm just going to take some recognizable pointer and cast it. And I'm 33, so let's see if that works. Just put that at the end. So we need pair data to describe that. And we already have a type lying about, so that works. Let's see if this thing actually does what I hope it does. Yep, it did. All right, that's a lot of typing. Just let me take a breather. How's everyone doing today? Let's see if there's anyone I know. A few standbys. Actually going to define this. No, rather than just forwarding it, I should make an error somehow. Alright. I should probably have some commas as well. Yeah, doing pretty well. Taking it easy. Alright. Maybe there's a better notation for that. Like, yeah, let's do that. Let's use this pseudo Lisp keyword notation just to suggest which are primitives, or like which are names. And then aggregate. Yeah, I think I like this better. It's a little more visually parsable. Dwarf call frame information. That sounds like fun. Alright, I should verify that this works still. Oh, okay, I think this is pretty much what I wanted for the printing. And I'm also happy to see that we were actually good. I guess I was about to test these accessors, but I guess we got to test them sort of for reals in writing this thing, and it's pretty nice that they just worked the way I expected them to. All right. Okay, I need to test casting. So actually, let me go and fill in a bunch of the built-in types that we're missing. So we need some UN16 action and some int8, int6, int16, int32, and int64, and some float and some double. I think for now we're just going to say, which is not, I think, totally true, but we're saying that I don't know if you guys know this crazy thing about signed versus unsigned chars in the C standard, but there's a surprising amount of leeway allowed there, and apparently some machines actually take advantage of it. So this is definitely not a universal statement, what I wrote right here. But for the machines I care about, it's true enough. All right, let's see. So we have to fill in the 16s and the signs and the floats. Maybe the way to do this. Okay, I guess I'll just do a bunch of typing, which isn't the worst thing in the world. guess I'll also make one for floats and doubles. Too many initializers. Did I not update this? So, okay. Alright, so I think that's it for these. And then we need to, I guess the main thing we need to do is all this garbage. Okay, this is going to be a lot of typing. Let me see if I can define a macro or something. There's a sense in which there has to be n squared amount of stuff, because that's how many potential differences there actually are that need to be converted between, but it can still be less manual than other, like we could have a macro that defines all these almost at once. So if we have a macro that does let's see, so this one would basically, it would take source value, so it would do all of these. Actually, it will do all of them. And then the only thing I have to do is define the source value. Which is a heck of a lot nicer. Well, let's just see if that works first of all. Uninitialized used. Oh, here. Okay. templatize that even more. Yes, we can. Convert. So let's take a label and type, and then we do case label and type source value, type source pointer. And then you just have to do convert Ceno U into it. Yes. Okay, Visual Studio auto-indenting is really pissing me off here because it doesn't know what I'm... Can't parse through the macro, of course. Actually, I'm going to call that case. Let's make sure this all checks out. So we have some source pointer to that one, declare that. And we just, okay, so that's wrong. Eight, 16, 32, 64, float control. All right. Well, I guess we should start doing some tests here. So we should be able to, kind of the interesting cases, or some of the interesting cases would be like float to int, and vice versa. So if that's the case, and we create a Ceno float to describe it, and then we have assigned int, and we don't assign it anything because we're going to write to it, so we just get the pointer here. Well, let's make it a signed thing to keep things happy. And then we should be able to do Ceno cast if. convert from data. We should be able to okay. Source type has some garbage thing. Let's go to call stack. That's wrong. So that means I have a typo. It says size 2. It should be size 4. So I have a typo. Yep. Okay, still failing. I wonder why I don't have... Well, I guess I do. Let's see here. So, okay, so this is still in the source dispatch. So the source type claims to be okay, it's still like the pointer 1, which is not good. Ceno float, which has size 4, and has that there. And this one still has size 2. Okay, I'm losing it. Just replace one typo with another one. And it's still on the fucking fritz. Okay. I'm a little confused why my... Until I go back here, I don't have any good idea about what this actually... So let's see here. Okay, so int32 it now has size 4. And it's a primitive. And this is what I would expect as well. Maybe because this is uninitialized, and it's actually trying to read from it. Why the fuck am I not getting proper debug info here? Maybe just because they're not valid pointers. Okay, that's not the right call stack. Up here. What the fuck? Oh. Okay, now we're at least on the other case, which I never handled. There's something super weird going on with the debugger today. Because the point at which... Yeah, I really don't know what was going on there. Alright, and then for this one, I guess we'll do the same. Kind, type, and it's going to be like this. I should have some more uniform naming scheme. Like rather than, okay, I will replace underscore value by underscore t value. And then, well, in the other case I have to fix this, not with float, but with the others. Okay, because then we can do actually I should just copy these up here. Okay, that worked, and it actually did the right cast. Lo and behold. I don't know about you guys. In the absence of a better macro system, I'm pretty glad we still have old school preprocessing every once in a while for this sort of I mean, yeah, this is there's a sense in which I guess you could use templates for the same thing, just as well, but you can't, like, there has to be some level of static code expansion for this code to work, because it essentially has to, in theory, handle every pairing of source and destination. So whether you use templates or macros, you have to get the compiler to actually separately consider all the n squared cases. Okay, we should try the other way as well. So if I now, and once we've already set up the data descriptors, the Ceno data descriptors, of course we can assign to the original data and redo. So for example, we could do, let's do this one. If we then do, I don't know, 1, 2, 3, and we now cast from I data to F data. This should do the trick. 1, 2, 3.0, 0. So that all works. All right. Maybe I should. I mean, I'm convinced it will just work, but I should do some examples to show how fancy you can get with nested recursive types and stuff. So for example, what would be, I'm trying to find some semi-plausible example. I mean, this is straight out of the shitty OO handbook, I guess, of real world similes, but a building has it has let's say 4 doors, and it has a title. I'll just call it that. It has a width and a height. Windows also have width and height. And maybe they have a type, and there's up to apparently up to 64K different types. So let's say there's 16 windows, and doors just have heights, and there's fewer of those types. And windows have, yeah, I don't know. We need like another level of, maybe there's trim. Let's say windows have 4 trims. And a trim has a length. I mean, I'm just trying to make some random shit up here. And we should now be able to generate type descriptors for all these things. So Ceno data, or Ceno type, trim type, is an aggregate called trim. Size of trim, count 1. It has 1 field. And these are the fields. Field number 1 is a float. Oh wait, so what's the, I'm trying to remember the ordering for these. Type, name, offset. So type, name, offset. Cannot convert from. Because I only have one thing in there. Oh, I shouldn't take that. Ceno uint16 type. For trims, and this is a little bit interesting because they're contained by value, pass in the trim type, we call it trims. Oh. We actually have to create a separate type called window trims. And this type is it's essentially trim type, but with a count of 4. Window trims type. Convert from initialize of list to trims. What am I doing wrong here? Oh. I think we're going to kill the doors. I'm getting tired of typing, honestly. Okay. We also need a building windows type, which is the same as window type, but with a count of 16. And then we have this one, which is a building. Ceno type. I think I should probably have some predefined Ceno chart pointer. Alright, that's enough typing to last me a year. The reason I set this up is I want some sort of fairly nested case we can return to for testing. So if I now make a building, let's say we set it all to 0, we should be able to print it. Alright, we have to make building data. Okay, so that didn't... Let me just make sure it's not skipping stuff that I didn't think about. Okay, so it's printing an empty aggregate. I think it's because I didn't fill in the fields, which is required, and there's 1, 2, 3, 4 fields. That crashed, no doubt, because oh, I never filled this one out. Okay, let's do that. I don't think I'm going to use macros for that because it's not an n squared deal. So you, helpful compiler. Okay. That looks reasonable. Maybe I need to add some line breaks in my printing so I can see what's going on. I guess we don't need that if we're doing... oh, that's for the types. I don't think we need it for the types. We need it for this. I guess the indentation will be pretty off, but for now we can probably live with that. Or maybe not. You know what, I'm actually going to do an indentation thing. I think that's fine. I guess we should make this like a... this one should be the helper. What's the skip? Oh. It's called a print nested. Yeah, that's a little extreme. So I have no idea what the fuck this is. Is that the indentation as well? doesn't look right. So we print indentation at the beginning. So starting whatever, and then increment the nesting. I guess that's not really what we want, is it? Because this thing has already been indented at that level. Maybe we do these on separate lines. So we do it like this, and then a new line, and then it does that, and then we... Okay, that looks better. I'll actually add an extra level because it looks good. Okay, for for arrays, don't like the fact. No, I guess that's fine. So Windows is an array. Yeah, I guess this is fine. I think we should maybe make it 2 because it's a little aggressive with as much as I'm doing it now. Yeah, that's better. Alright. I guess the... Okay. I think that's it. So the thing I wanted to test is now we have a way of printing that. We should do like a before and after, basically. So before and after. The after will be basically me taking... So I will start with a... let's just call it data. And I will start with it initialized from the building. And then I'm going to traverse the building data structure. So I will go to Like for example, let's start by changing the height of the third window, or index 3 window, fourth window. The way we're doing that is we use getField. Ceno getField index data type, and it's called Windows. Let's just make sure that doesn't assert. So that works. So now we're pointing to the first window, or in other words, the base of the Windows array. Now we can say, well, we actually want to navigate down to the third field. And then we can say, so we're the third window, and now we want to get the height. Still works. And now we point to the height, and so you could obviously do this through a generic text-based parsing and assignment interface, but so first off, let's assert that this is Ceno float. Oh yeah, I have to do that because it's value. So that still works. Which means that now we can do this and say we want the height of the fourth window, or index 3, to be equal to pi. We should now be able to, you know what, let me make this a whole lot smaller. Let me make this equal to 8, actually 6. So 1, 2, 3, so you can see right now the height is 0. Oh, no, so now something went really wrong here. Oh, I think I know what it is. I forgot to update the 16 to the new number. Actually, the easiest way I can do it is to try to remember what is. I mean, I could just. I thought count of was. Am I high? I thought count of and offset of were part of the same. Okay, well. Alright, we'll just call this 6 though. That's fine. And then if we go, there should be, so this is the number 1, this is number 2, number 3, 4, 5, 6. So there should be no more. And we went in and changed the fourth, i.e. index 3, height to be pi. Or sorry, yeah, it was the fourth one, index 3. So yeah, so this was set. So that's pretty exciting. If we wanted to then go from here, and we could actually descend further. So, or what we could do is we could say, let's make a height data. Let's make a copy of this in here, but then we want to continue the descent into the trims. Okay, that didn't work. Why did I? Oh, because this one. Okay, so the other one now is descended into the trims, and we want to descend further into. Okay, so it only has one field, that's the length, which we will get. we should assert that we're now at a float again. And let's set the let's set that to like, I don't know. Yeah, I don't know. Like this. That was misspelled. Okay, so if we go and find pi, which should still be there, you can see that the first trim now has length that. The other thing I should mention is we actually, so this shows that I didn't do a get elements from trims, I just did a get field. And that works because of this identification between single argument values and arrays. But we could also do this and say, actually, we want to go to the third trim and set that's length. So now it's down here. So anyway, I think this is like a good way of doing this stuff. Obviously, the printing is mostly for debugging, but it shows how you can do a sort of guided traversal of the actual, based on the type of the raw pointers, and eventually get to some base types that you can actually make sense of directly. Okay. Yeah. Holy fuck, that's like 500 lines of code in an hour and a half. That's what happens when you're writing this kind of menial crap. But now my wrists hurt. I'm curious. I'm just going to take like a breather for a few minutes because the next thing we're going to do is pretty heavy, which is so now we basically did data, to be honest. Like, this is everything you need from data, more or less. One thing you might want is something, if you think of print, that's sort of one side of it. The other one is read. It's also useful to have a way of parsing things. So you can do, I mean, I don't know, like if you have like a Quake style console for maybe manipulating your game variables, that might be useful. If you have a debugger, you want to be able to, basically, if you think of this thing, Ceno print as printf, you want scanf to complement it. But if you're doing a graphical UI to manipulate these things, instead of these text-oriented functions, you would of course have something else to replace it. But the same thing, basic thing would be true for those, which is that you do this traversal where you deconstruct the type on the way down in the recursion, and then once you hit the bottom, you can do some primitive thing depending on the format. So for text, you do printf. You just lean on built-in printf for doing this. And if this was like scanf, you would bottom out at scanf, I guess. Although no one uses scanf, so. Alright, let's see if someone tweeted at me. Actually, that's the wrong window. So that's, I'm always paranoid about my my non-incognito window on stream, so I'm just going to bring that up. Alright. Does anyone have any questions so far? Like, I'm not sure if you guys have ever used these generic kind of data representation systems. I would say that one thing that I consider a distinct advantage of this system is this whole sort of accessor or access path approach, where you know, you start with existing Ceno data values and get new ones that sort of traverse the tree of types. Well, it uses the types to drive the traversal, but essentially it's also doing pointer arithmetic on the way down in order to do all the to place all the pointers at the right location so that you can eventually read from them and write to them. Nothing, huh? I guess the other piece of this is like if you don't want to manually construct all this data to describe it, how do you get it? Um, and there's various ways you can do that, right? Like you can parse PDBs. In fact, I may do that later because I actually wrote some code like last week, which was just some test code, but it told me that you can very easily, using debug help, you can very easily get this kind of data out of PDBs, and then you just have to construct these data structures to represent it. Did I ever test dereference? I should probably test that. No, I didn't test that, so let me just do that. It should not be an issue, but it's worth testing. Um, so if I have a pointer to this, and the thing I'm storing is not P itself, but actually the pointer to P. Um, right, then we would like to be able to write to, so if we do this before and after, we would like, well, actually there's two steps, I guess. Um, Basically, we can go from P data to B data like this. And then from B data, we should be able to verify that it actually has what we expect as the type. And so if we set this to 42, yeah, you can see that works. So this is for doing pointer dereferencing. So you take the data descriptor for a pointer and you turn it into a data descriptor for the dereferenced element, which involves, it's not, so unlike the other get element things, this thing actually does dereference the pointer. So it's not just doing address arithmetic, and because of that, like if this thing is invalid, it will crash and stuff like that. But anyway, so yeah, that works too. I should put this earlier since it's a more basic test than this aggregate testing. So Tom's saying, I generated my structs with Python code as part of the build process. Comprehensive. Yeah. So what do you do that's not as comprehensive? Is it just that's maybe you don't have all the primitive types, or? But yeah, I think actually the question of how you parse it and or get it out of whatever other thing you're doing is almost orthogonal, because you're gonna, like, what I wrote here is actually like really general purpose, but depending on the use case, like if you're writing a debugger, you're probably going to get this from a PDB file. If you're using this for a game reflection system or something, you're probably going to have something to drive the reflection, right? Like you maybe have, uh, maybe it's manually filled in like I'm doing it, or maybe it's based on a preprocessor, or maybe you have a Clang plugin or whatever. I see. Yeah, that makes sense. Okay, I think I'm just gonna glance over my code as I'm wont to do when I'm done typing a bunch, just to make sure I didn't do anything stupid. Um, and then we'll move on to functions, foreign function interface stuff, which is a little bit more of a pain in the ass. But yeah, if you look at the basic system here, um, honestly, what I would call the basic system stops at this line, which is, it doesn't. Ceno cast is a little bit advanced. I do think it's actually needed if you want to do a general purpose system like this. But if you're just doing serialization, you probably don't need it, because you're always going to know what you're dealing with more or less. Um, but even including cast, and not the print stuff is purely diagnostic, so I wouldn't include that. That's like 200 lines of code exclude, and there's some stuff at the end. So that's 200 lines of code for a less than 200 lines, 180, I guess, for like a completely expressive like this. Oh, one thing I should mention um, is that this works with unions as well. I think I mentioned in passing that this whole notion of an aggregate is not specialized to structs, so we should actually test that in case that's not clear. So if you have a union, and we can do the classic, what's it like, float UN32. We can do this classic trick here, and then say we let's call this FU. And let's say we assign through this one, and then we have Ceno data, or Ceno type rather. Well, so we need Ceno fields, and this would be the, actually let's just call this float n32 fields. Field 1, what was the order? Types. So first type is float, and then name, and then offset. And interestingly, when we use offset of on a union, of course, the offsets are going to overlap, and that's also going to be true in my thing. So that's just doing the obvious thing for this actually works. Ceno type float UN. Okay, should really start remembering. What is it? Aggregate name size of. Okay, aggregate names. That's float size of. And there's one of them. So if I do this, and we do a print. Sorry, so we first have to create a data descriptor. Okay, that didn't actually work. Or it was empty rather. Oh, it's because I didn't set the fields, which is not the first or last time. So do you see here how it's printing them out as separate fields, but they're actually aliasing each other. Um, they're aliasing each other in memory, but the cool thing is the system doesn't care. It really doesn't, um, because of the way it's set up. As far as it's concerned, they're just fields, and they have some position, they have some offset relative to the parent, etc., and it all just works. So yeah, that's pretty cool. So you can do the usual tricks here. So for example, um, so let's do that, and then if you manipulate it from the other side, um, like this, now you're going to see you have the size you entered, but F is going to be whatever IEEE 758 equivalent of that thing, which I guess is just 0. Well, actually, so I can show you a trick, I guess, which is if you increment, lexicographically floats and ints are identical except for sign. So you can see that if I increment by an integer, it actually increments sort of, well, to be completely clear, I think for a non-infinite or weird, for a finite integer, the successor in integer terms is the same as the successor in floating point terms. So it's the nearest, it's the next greatest representable floating point number, which means if you increment by some relatively large number, you're actually going to see the digits change. And anyway, I guess it's a nice little demo. You can see it went from 314 to 314 2384. So yeah. But yeah, so we can do structs unions, we can do arbitrary value arrays of stuff, we can do pointers, we can do all the primitive C types. So this is basically, if anyone can think of features I'm missing, I can't think of anything. I mean, there's obviously, like, if you want to populate this data, that's like a separate system, but this thing is pretty much done as is. So unless people have sort of things they feel is missing, I'm going to move on. Like the stuff you could obviously do is, like I said, rather than just having prints, you could have scans, you could have UI that does the equivalent of that. But I really just care about having the data there and having the basic functions you need to manipulate the data. Okay. Cool. All right, foreign functions. This is where I get a little bit out of my comfort zone, but hopefully not too much. All right, so what we did is basically foreign data, and now we have to do foreign functions. Foreign functions is, in a lot of cases, what people think of as the foreign function interface, but it's pretty rare that you can actually call a function in a non-trivial API without manipulating its data. So the data is sort of a prerequisite. So for example, if you're using the Win32 API, most of the functions you're calling take structs as arguments through pointers. So you need to be able to populate those structs to even call them in the first place. And so the foreign data stuff, even though people normally don't call it that or even bring it up as a separate thing, it's really a basic prerequisite. Even though it's also useful in its own right, it's also just like a basic prerequisite for actually calling interesting functions in third-party C libraries. So for calling functions, the big thing you're essentially doing is you're going to want to translate from some kind of uniform calling convention into whatever machine-specific calling convention is relevant to the function signature you're trying to call. Um, so, for example, maybe maybe so RAX, the compiler undoubtedly has depends a bunch on the operating system and the processor, but there's conventions like maybe the first four arguments, if they're integer or float arguments, maybe they go in registers, but otherwise they go on the stack, or anything that's longer than beyond a certain number of arguments, they go on the stack. And with x64, there's this convention about structs, that well, we can go and read it, but basically, structs have to get pushed by the caller, and then they pass a pointer to the struct they're passing in. But notably, the pointer they're passing in is a pointer to a temporary copy that they just pushed on the stack themselves. They're not pushing, it's not like the semantics in terms of the callee are not passed by reference, because you can't observe changes to the original copy after the fact or anything like that. So it's a separate copy, but it's passed by pointer rather than by value in registers or scalarized or anything like that. So you have to somehow figure out how to map whatever standard calling convention. And by standard calling convention, what I mean is something like in Ceno, we have the Ceno data structure, which takes a pointer and a type descriptor. A uniform calling convention, for example, would be, here's an array of pointers to all the arguments, right? So that would be the calling convention from Ceno's point of view. Now whatever the machine-specific shim has to do is do the right machine code to transform those pointers into, read the data that needs to be read or whatever, and put it into registers in the way that the machine expects and the calling function expects, or the function being called expects. So that's a little bit messy, and you can't really do it. You can't really. Well, let me point to the difficulty with doing it purely in C without any assembly code or code generation or anything. We already had this combinatorial mess with cast. If you think about what went on here, we had essentially n squared cases where n is the number of different basic types. And we mostly got that under control, at least in terms of the source text, or the amount of stuff we had to type by using a macro. But there's still essentially n squared amount of expanded text here. If you have a function, and the function can have an arbitrary number of arguments, you can't, in theory, let me give you an example. Suppose you wanted to create this kind of transformation that goes from a standard calling convention to the machine-specific calling convention. You can do that for a specific argument. So, for example, call. So suppose you have a function. I'm going to write it on the bottom of the file. So this is temp code. Suppose you have a function pointer, and the first argument is a float, and the second one is an int. And you want to create sort of a uniform call gate for that. You would do something like this, let's fp type, and then you would do fp type fp. So you take the function pointer you're supposed to call, and then you get the arguments. And essentially what you would do is you would say, well, argument 1 is going to be a pointer to a float, so I'm going to do like this and dereference it. And for the other one, we're going to skip by this much to get to the int, and then actually, I guess we said there are pointers to that, so really it's pointers to pointers. So this would be like f pointer is args1, and I pointer would be args2, and then you would do this. aside from me not being able to spell, I think this is roughly correct. Yeah, so you can see something like this. Now this created a call gate, or a, I don't know what the right word is. Let's call it a call gate. It created a call gate from this standard parameter passing convention where you just pass pointers in an array into by essentially explicitly instantiating this specific combination of types float and int in that order. It instantiated that transformation from the generic convention to the specialized convention. And so let me just show you. I want to show you the assembly code for that, I guess. That would be a good starting point to talk about this. So we should have like f. Actually, let's just say it returns a float. Actually, that's a good example because part of the calling convention is also that we have to return the argument. And so the way, by convention, we assume that arg0 is where we're supposed to put the return value. So we do it like that. And f redefinition. And then so return value f argument I argument. So let's say f argument is this, and this is that. And then we have the arguments, which is just something like this. And then we can do that. And then we can verify that the return value, I'm just going to return early so we don't see all the junk while we're testing. The return value is then going to be, well, let's try to look at it before we run it. It's going to be, well, 314 plus 120, 123. So yeah, so that worked, right? Does that make sense so far? Like basically, we would want something like this interface where the thing we pass into the generic call gate is that we pass in an array of pointers to both where we want the return value to go, but also where the various arguments can be fetched. And they're just pointers, so we don't have to worry about them having a heterogeneous size or anything. And then the job of this call gate is to take the function and this array of pointers and basically do the deed. Now, the thing I want to point out is that we did this just for a specific combination of argument types and return types. But there's not a finite number of them. It's not even like a large number. It's like an infinite number. And even if you truncated it and said, we're only going to support, I don't know, like, and there's also struct types and stuff that make this complicated even more, but you can just see that it kind of gets out of hand. The combinatorial explosion, even if you truncated it like we're only going to do functions with at most 5 arguments, it's completely out of control. So you can't do this approach I did with a cast of just basically having macros and trying to generate a bunch of combinations. It goes completely apeshit if you try to do that. But I want to show you what the code actually looks like at the assembly level. So if we run to cursor and then this is not optimized, but it's still using, it's running in debug unoptimized. So, but it's still using the same general thing. So you can see that we're passing 2 arguments. That we're passing the pointer to args and the function pointer func, and then we're entering this call gate, and there's this indirection, and then it pushes. Was that really? Hang on. RDX and RCX. Okay, I thought it was AX for some reason. So yeah, so it takes these 2 arguments, puts them on the stack, pushes the existing frame pointer, makes room for what local stack space it needs, um, stores the current frame pointer, makes a copy in there, puts in a constant, another constant, and then does some stuff. Right, so for this, okay, so here it's basically just doing pointer arithmetic and some loads. The thing I want to emphasize is that it's ultimately it's leading up to this call instruction, and in order to call this function with a known signature, namely, float return value, first argument float, second argument int, it has to put it has to put stuff into the right registers. So for example, you can see that the first float argument goes into XMM0. So that's like on 64-bit, they don't use the FPU registers for that anymore. So the first argument goes in here. First integer argument goes in RAX, I guess. Yeah. An EDX F pointer. No, that's not true because it puts that in there. I see, and then it reads from it. So EDX contains I. Okay, so EDX contains I. The first R, which is also consistent. Like, by the way, I'm shitty with x64 calling conventions, so I'm learning on the fly because I've never actually had a chance to really bang my head against them and memorize them. But if you look at the original call stack, you can also see the first argument was also RDX. So I guess RDX is, wait, I guess the second argument. But arguments are there's sort of a back to front order with them. So anyway, but you can see that basically the trick is, aside from reading from those values, which itself also requires some work, it has to permute everything into the right registers, and in some cases into certain stack slots, because not everything can go in registers before actually doing the call. So that's really the challenge. And I guess I have to go read the docs a little bit to figure out if there's a reasonable way of handling that. I'm sure it'll definitely require assembly code, I'm sure. So okay. So 4 registers. Any argument that doesn't fit in 8 bytes or is not 1, 2, 4, or 8 bytes must be passed by reference. Okay, no attempt to spread a single argument across multiple registers. That's like, there's no scalarization at the calling convention level. Right, no FPU stack, I knew that, that's what I mentioned a second ago. But, well, you can use it within a function, but it's not part of the calling conventions, it's volatile. Right. Arguments are passed in RCX, RDX, okay, so I should start taking some notes on that. 16-bit arguments are passed by reference. What about 32? Okay, let's go read the stock. Volatile. Right, so I remember that vaguely. why I'm using WinMain. It's just a habit because I almost never use the console subsystem, even if I'm doing things that are vaguely text-ish. But yeah. Arguments 5 or higher are passed on the stack. All arguments are write justified in registers. When they say write justified, I assume they just mean sort of zero extended or something like that. Yeah. So if you're passing a 1 byte value, so you don't even have to set them to 0, if you will. I know that, yeah, I mean, the problem with console apps in Windows is that printf by default doesn't go to the debug output, so then you have to reroute them, and it gets kind of ridiculous. Okay, so this is important. So if if integer register n is passed, float register n is unused, and vice versa. So, for example, if rdx is used for passing a parameter, then m is unused. Okay, so that's good to know. Hard to hear my voice over the other guy. Is my volume not that loud? Anyway. Okay, now we go full Hall of Mirrors shit. Alright. Let's see if I remember how to do assembly programming. It has been a while. Can't remember if they have a shortcut here. Nope. I guess we will call it call.asm. Oh, that's another Ceno. I forgot I had two things called Ceno. That's really awkward. Two things that are completely unrelated, apparently. Alright, well, that's not going to get in our way too much, hopefully. Right, so add this, and then see if I remember how to do that dance. Okay. I have not used Masm in so long that I will go and read the find docs. Actually, I'm not working on a sample profiler anymore. That was like yesterday. Pure C project, mixed. I wonder if any of these old assembly samples are still workable. Yeah. May not represent best practices for current development. Are you saying I should not implement my utilits algorithm in assembly? Where's the actual code? Okay, I guess that's not there. Maybe I can find some. x64 massum example. Okay. Required at end of file. Why does it not consider that end of file? I have to go to the bathroom, by the way, one sec. Alright, let's see here. .64. Well, this is not going to compile, I guess, because it's almost like this version of the file. Yeah, it's not it's not the same file. Oh my god. Alright. Okay, let's just do a dummy function. Let's go and read these calling conventions and figure shit out. Types and storage, register usage, calling conventions, stack usage. So much stuff. Okay. Okay, return value register. So if I put in a value, but this is probably not even enough because of all the like I'm not even sure what I have to clean up as a caller in x86, x64 rather. Every function. I guess I should just just look at the code here. Oh, that should be. Okay, this is some breakpoints. Okay, so let's see what it has to clean up. So let's see. So it pushes these two, makes room on the stack, initializes the new frame pointer. Then I want to see what it does down here to return. So because the stack grows down, when you plus, you actually cut stuff off the stack. So basically this is resetting the stack pointer to, I guess, to here plus the, oh yeah, so it's 128 here and then 20 here. And these 20, I mean, that's like 32, right, in decimal. So actually, I guess I can just, if I do like a really, I think this simple thing I did here actually just works. So if I do a prototype, does that work? No. So maybe I have to do something to, what was the 64-bit one? Is that why? Okay, that's it. Okay, so that actually works. All right, let's think. So we need a notion of a function signature. And there's a bunch of argument types. There's a return type. I guess there's a name if you want it to be annotated like that. And that's really the main thing, isn't it? Technically there should also be like a calling convention. I'm just gonna say, I mean, I'm only really honestly concerned about x64, which has mostly one calling convention, which is whatever the generalization of the old fast call was. Okay. Okay, I believe that's it. So in order to call this, so to call a function, we are given return pointer and argument pointers. Oh, we also need an actual function pointer, which is pretty important. Screw this name. Doesn't have any value. So yeah, we have a function pointer, and sort of conceptually what we're doing is we're doing, if it wasn't for the fact that we don't statically know what those types are, we are basically doing this. That's the very sketchy, high-level function this thing fulfills. I guess let's start simple. Let's assume everything is a uint64. So that really simplifies things. And in theory, we should be able to do something not too crazy. How do I get massim structs? I'm trying to remember how to get structs over in massim, so I don't have to manually do my offset math. Okay. Fuck the calling convention for now. Just don't want to think about it. What is the equivalent of a 64-bit or pointer-sized thing? Can I just do dword pointer? Does that work? Seems so. What's the other one? Argument count. Does qword work? Doesn't matter what these are. Okay. I guess I should do a test to see how how, because passing structs, they're passed by reference, I believe, by the caller. So oh, just do something to force the code to be generated. Alright, that's not it. Fuck that. So I should be able to say, call this with something like that. Oh, no, that was right. So what was I complaining about before? Cannot convert from void star to argument 3. Okay. Well, let's see how this thing does the call with the struct argument. So loads the pointer of defunc into RCX. And according to my notes, RCX is the first argument. I see. So it actually just passes that in directly. I thought it had to make a local copy to pass it in. Alright. I guess that's really convenient. Well, I could also just do this, now that I think about it, which I probably should do anyway, to be perfectly honest. Alright. Let's have dummy function basically return one of these fields that you pass in. The chance of this working is pretty low. So load from RCX. So how do I use the struct notation? Okay, this macro assembly shit is way... I probably shouldn't use it, honestly. Yeah, this is some Weird shit. I should just do the address arithmetic myself. I thought I would be fancy. Oh, I can also do it here. Maybe that's the better way to do it. So, Ceno function putter. Instruction operands must be the same size. So function pointer is a D-word putter. That doesn't make sense. I mean, a pointer is a pointer, right? Okay. I'm just going to remove this putter. I don't think it did anything. I think it probably did something other than what I was expecting. What was the print even coming from? Oh. Okay, so that does return that. What if I specify this? Okay, that actually works. Yeah, I mean, honestly, usually if I do assembly, it's been historically inline assembly, so all this macro assembler stuff is not something I'm really used to. And maybe I should just forget about it and do my own offsets manually, but for now this seems not too unbearable. I guess the main thing we want to get right is just the field sizes so they can do the offset math for us. So, okay, let's try to fill in a little bit. Let's try to model like an addition function. So, add, which takes x and y and returns it. And so, for now, we're just going to pass in null pointers because we're just going to assume a certain layout, a certain signature, just to get the calling conventions right. I guess if we pass in the function pointer, it's going to be something semi-reasonable. All right. Okay, so I guess what we want to do ultimately is to do something like this. Must have size. Okay. So we can at least set a breakpoint and see, like it's not going to have any. Oops. Yeah, this is actually what I wanted, right? So this contains the address. Presumably, if you pass an argument, it will. So if I, okay, so that will actually hit my breakpoint. So that's fine. Now we just have to set up the calling conventions. So suppose that so it's going to take this, and then it's going to take a return pointer. It's going to take the argument pointers. also remind me what the things up here are. So first argument is RCX, etc. Right. So the only thing we really need from that struct, given that we're not parsing things right now, is that field, so that's fine. And then, let's see. Everything else is volatile, so I guess we can... Also, what else do we actually need? Okay. So argument... So RDX is the second argument, and that's going to contain the return pointer. So once we're done, the argument is going to be an RAX, and we basically want... Although, I mean, that's going to be destroyed by the call, but we can always, I guess, arrange that. RDX should get the return value. And, okay, maybe we'll do just return value forwarding for now. But I wonder if you can actually do this like that. So for now, it's just a function that returns a constant, let's say. Okay, what do comments look like? Yeah, it's good old semicolon. Does not take one argument. Well, I guess that's actually true. So we do want to use one argument, which is return value. Okay, so that worked. Let's do arguments now, I suppose. Which means, let me just sketch it out for my own benefit. RCX, RDX, second argument. So it means I have to read, so currently, so argument pointers is the third argument, which means it's R8. Okay, let's just write that down. So argument pointers, RBX, let's read the first argument in there. I don't even know which of these are. So what was it? What was the thing about volatility? Okay, so I can use R10. I'll use R10 for that. And then 8 for the next pointer. And then the first argument first argument is Q put our R10. Then we call, and we pop, and we get it back. So let's add 42 or okay, so this is where probably I screwed up the calling conventions because I didn't read the docs carefully enough. So already accessed the second argument. Can I actually... Okay. So RDX is currently... Let's look up in the stack here. Okay, I think that's right. So it gets pushed. And on the stack. Oh, what was it? I have to make room. Yeah, so it actually assumes that I've already made room for the, for it to save RDX and RCX. So that's one problem I have. I guess I can see how if I call this directly, I can see how it does that. No, it really doesn't. Or maybe the function as a whole has already made room. Yeah, I think that's it. So it says I have to make room for, what did I write up here? I'm going to make a copy of these. Allocate space for at least 4 register parameters. So that's 4 times 8. That's 32, which is Let's step through this. So RCX, yeah, that doesn't look right either. Because that, so RDX is the return pointer. We probably shouldn't use this to save it in any case. But, oh right, this one's non-volatile, so I actually don't have to save it for one. I have to make space. I have to make space for this. So the caller can put it in there. Maybe I should also save those two out. But for now, let's see if we can just make it to the end of the call. Let's see here. I haven't even loaded R8. What am I? No, that's not true. That should be the argument. So, third argument. Yeah, that looks reasonable. So this would be the first pointer, right? Which also looks reasonable. This would be the second pointer, R11. So R10 and R11. Yep. So they both point into the stack. And now I guess that's the part that doesn't quite make sense to me. Oh no, they are like 42. I shouldn't use these big values. I should use like something small that I can recognize in hex easily. I'm so rusty with this shit. Alright. So we have 3 and 7. And we're now making space. But it should be this much space. Okay. Push, push. Make some space here. Pop, pop. Back up. Oh, RDX is 7. Guess I'll make my own space in the stack. Let's just do a bunch here. Let's see, so that's 32, that's 48, minus 8 is 40. stack. I don't even know if the stack is in the same place or not. Actually, we only care about the number 7 is a little conspicuous. Did I just not? Okay, I fucked up the stack as well. Great job. Okay, so 7 is this thing. I should really just go read the docs. I think it's break time from stream for me to just go and bone up on calling conventions and fucking assembly language or x86 stuff. Or x64 rather. But I think the general plan of attack, at least for integer arguments, is, you know, you put as many, you put up to 4 in RCX, RDX, R8, R9, and then you make space for any overflow on the stack and copy them there, and then you call the function, and then on the return you copy RAX through the pointer to the return value. And that should be it for that. We'll figure it out. I just need I shouldn't like do it ad hoc, sort of like just fumbling along like this. I should actually just go and read, which is not very entertaining to watch on stream. So anyway, I'll take a break and bone up on that, and hopefully be back either tonight or later this week to finish this stuff up. But yeah, hopefully the data portion of this was pretty useful and informative. I honestly, like, I think this is not just a showpiece. I actually think this data, the Ceno data thing, is something I'm going to use going forward. I'm pretty happy with the interface and how tight the implementation is. So yeah, thanks for hanging out.